In our last video, we looked at how we can calculate the work using a formula that involves the force multiplied by the distance. And the force must be in the same direction as the distance, so we can use the cosine of the angle to help us calculate that. So using that formula as an example, here we have a 50 Newton force multiplied by a distance that it's traveling of 8 meters to give us 400 Newton meters, which is a joule. So we did 400 joules of work. Likewise, we could graph that. Similar to when we had a displacement graph and we calculated the displacement from the velocity and the distance, we can use a work graph to solve this problem. So here we have our 50 newtons of force being applied consistently over an 8-meter distance. The area between the curve and the zero will solve the problem of the work. So here we have a height of 50 newtons and a length of 8 meters. So 50 times 8 being 400 joules. So using the area equals the work. Well, that doesn't seem like much of a help. But what if we had a problem where the work varied? Or sorry, not the work, but the force. What if the force was not consistent? What if the force wasn't the same throughout? How could we do it? Well, we could simply do the same thing. So here's an example of here we were starting and we weren't pushing very hard. We had a force of 0. And over a period of time, we pushed harder and harder and harder and harder. And eventually I have an object that moves 6 meters. So at the beginning, I was pushing with a force of 0. And at the end, I was pushing with a force of 100. How much work was done? Well, the work done is this area. And of course, that's the area of a triangle. And the area of a triangle is 1/2 of the base times the height. So it's 1/2 the base. The base here was 6 meters. And the height was 100 newtons. So the area is 1/2 of 6 times 100. That would be 300 joules of work. Here's another scenario. Maybe you were pushing with a force of 30, and then you had a friend help you for a moment, and combined you push with a force of 50. Then your friend stopped pushing, and you push the object the rest of the way by yourself. Okay, so we've got a variety of different forces being applied. Well, to solve a question like this, the easiest thing is to break it into pieces. And, you could break it here, you could break it here, you could break it here. There's all kinds of things you could do. I think I'll break this one into 4 pieces, but I could have done this with 2 or 3. There's a couple different ways of solving it, but let me just say that I've got 4 different areas. I'll call them A, B, C, and D. And the area of A will be 1 meter times 30 newtons. So that will be 30 joules of force to solve for part A. Part B goes from 1 to 3. So that's 2 meters multiplied by 30 newtons. So that's going to be 60 joules. Area C, well, C is also 2 by 30, which is 60 joules. And area D is this rectangle here, which has a height of, let's see, that's 20 by 2. That's going to have an area of 40 joules. So the total work, the work total here would be the sum of all the pieces. So what do we have? We had 30 plus 60 plus 60 plus 40. And that's going to equal, oops, was the first one 30, 60, 60, 40. Yeah, okay, that's good. 190 joules of work done here. Okay, so we're just adding up all the pieces. This one's a little more complicated because this is not a triangle. I'm going to divide this one into two pieces again, see if that helps. I'm going to take this. This is a rectangle, and that is a triangle there. So, once again, I got two parts. I'm going to say A and B. And this part here, part A, let's see, that has a distance of 10 meters by 10 newtons. So that's 100 joules of work right there. B is a triangle. Remember, it's 1/2 the base times the height. The base here is 10, and the height here is 20. Be careful. It's going from 10 to 30. That's got a height of 20. So 10 times 20 is 200 divided by 2. That would be 100 joules. So my total here, my work total, equals 200 joules. And of course, there are other ways you could have done it. You could have found this space and subtracted that one if you so choose. There's more than one way of solving this. What about this one? And this is really interesting because on this question, this goes below the zero. Didn't write the zero in, but there's the zero. So this area right here below the zero, this is negative work. And it is possible to do negative work. We'll talk more about that another time. But that's negative work, where this is positive work. Okay? So we solve it the same way. I like to solve this saying that this is a height of 10. Just remember it's a negative answer. Or you could say it's got a height of negative 10. But it's a triangle, so that's going to be 1/2 10 times 2. Just remember the answer is negative. So that's going to be 10 times 2 is 20 divided by 2 is 10. So that's got negative 10 joules of work being done right there. This part over here goes from 2 to 6. Let's see, that's got a distance of 4. And then it's going to go up a height of 20. So that part over here is going to be half of 80. So that's going to be 40 joules. That's a positive 40. And then we're going to put the two parts together. And our work total is a positive 30 joules. Okay? So once again, the area of the curve, we can figure out the area between the zero or the x-axis and the curve. And by calculating that area, it is really, really helpful to solving that area to find the work done. And it's most effective when you have a problem where the force being applied changes. So if the force is consistent, use the formula FD times the cosine of the angle. But if you have a variety of forces, the easiest way of solving this is by using the graph method and finding the area. There is another alternative way of doing it, and that involves the use of calculus.